is discuss just something with projectile motion and parametric equations, and show you something which you intuitively know. Something you discuss in physics is what angle of inclination should you fire an object at to achieve the maximum horizontal distance. So here's what I'm really saying. You have some flat ground here. You're going to fire an object from some point with some initial velocity, we'll call it v0, at an angle above the horizontal, maybe called theta. And we know from physics that this object will trace out along a parabolic arc and then hit the ground over here somewhere. Okay? And this is the horizontal distance that we traverse. And the question is in physics that you try and ask is, hey, what angle should theta be given some fixed velocity so that you achieve the maximum horizontal distance? So I'm going to start by considering the velocities in the x direction and y direction separately. So if we look at this velocity vector v0, it has some components. Here's a horizontal component. Maybe you'll call that v sub x of t. All right, and then here's a vertical component as well. Okay, and that's going to be v sub y of t. Okay, all right, you can kind of see that. V sub y has a copy of itself over here, which is sort of nice because then you can see a nice right triangle and just do some basic trig. So what do we know, right? We know that the velocity in the x direction does not change as a function of time. That's sort of what you learn about in physics, right? As soon as we let go of this ball out of our hands, whatever it is we're throwing or shooting, the horizontal velocity doesn't change for the whole trip that this thing goes on. So we just need to know the length of this horizontal component. That would be v0, the length of the hypotenuse, times the cosine of theta. Okay, so that's your velocity in your x direction. Okay, and then when you go to consider the y direction, you have to worry a little bit, because in the y direction, obviously you could throw this ball upwards at some angle. It's got some initial velocity vertically heading up. So that would be sort of, it would look just like this. It would be v0 sine of theta. The problem in the vertical direction, though, is that as soon as you release this object or whatever you fired, gravity immediately starts to act on it, right? So you start subtracting off your velocity in the vertical direction, and the expression for that is going to be minus g, which is the constant for gravity, times time. I would encourage you to remember, like, thinking about units, and it sort of tells you why this makes sense. If you think about g might have units like meters per second squared or feet per second squared. It's an acceleration. Okay. So, no, right? Time is going to be just seconds, and you can kind of see when you multiply those, you get back meters per second, which is a velocity. So this sort of makes sense. All right. You also learned pretty quickly in your physics class, and also in your calculus class last year, right, that if you integrate a velocity function, you get a displacement function or a distance function, or distance traveled, right? So if we integrate each of these with respect to t, we would get distance functions in the horizontal and vertical direction. So if we take this first expression and integrate it, we get whatever you want to call it. We'll call it s of x of t. All right, it's going to be v0 cosine theta times t. Okay, and if we integrate this one, we get sy, which is going to be v0 sine of theta t minus 1/2 gt squared. And that's sort of that should look a little bit familiar to you, because when you had that 1/2 gt squared term, that is, because when you had your projectile motion equations written in rectangular form, not parametric form, you always knew that s of t equal to 1/2 gt squared, right, plus v0t plus s0. There are technically constants here of plus s0s. To simplify this problem, we're just going to pretend that this whole story starts at the origin 0, 0. That's what we're going to do and not worry about those constants. Let's keep our goal in mind here. Our goal, right? Let's just make a note here. Our goal is to maximize S sub x of t, I guess we'll say with respect to theta. We're saying, hey, what's the theta that's going to maximize our horizontal distance traversed? Intuitively, you kind of know that, like for example, theta couldn't be 90 degrees. If I throw the ball directly vertically above me, it's not going to move forward at all in the x direction. It's going to go up into the sky to some height and then come back down and hit the ground. You know, if you throw it at a very low angle, like maybe like 5 degrees above the horizontal, gravity's going to act pretty quickly and pull that thing to the ground. It's going to bounce along the ground, so it's going to hit the ground pretty quickly. So you can kind of make yourself believe that 45 degrees might be, you know, the nice answer to use. Okay, so this just means what we care about is the function Sx of t. But we need to do a little bit of thought about when this thing's going to hit the ground. First off, it has two variables. It has theta and t. I don't mind theta being there because theta is what I'm trying to maximize with respect to. So that doesn't bother me. The t bothers me. I don't like the t. I'd like to get rid of it. Okay. So we just need to have one realization. That when we throw this object, or when it gets fired from the horizontal, its height above the ground is 0. And it doesn't equal a height of 0 again until it makes contact with the ground the second time, when it comes back down and hits the ground. So if you agree to that, then we can solve for t in the second equation. Okay? What we're really saying is, when does this expression equal 0? Word when meaning solve for t. When does this thing equal 0? All right. Well, this is just some old algebra with maybe not a nice coefficient. Factor the t out. You see a t in both of them. So you get t times v0 sine of theta minus 1/2 gt. And that's going to equal 0. Okay. I claim that this very easy value of t you get right away, t equals 0, should not surprise you at all. Right? That's when the whole story started. That's when you fired the object or threw the ball from the horizontal. That's at the beginning of the story when the height above the ground was 0. This thing has to equal 0 also. So v0 sine of theta minus 1/2 gt equals 0. We just need to solve that. So v0 sine of theta equals 1/2 gt. Multiply by 2 over g on both sides, and you get 2 v0 sine of theta over g equals t. That's the time I'm interested in. This is the time when that object's going to hit the ground again. Okay? So let's keep in mind our goal. Our goal is to maximize the horizontal distance traversed. Okay? So we were trying to maximize the expression for S sub x of t, which is v0 cosine theta times t. But now we know something. We know what t is. And we're just going to sub it in. And this is going to require us to have a few more realizations. So v0 cosine theta times 2 v0 sine of theta over g. And that's where t used to equal. So if we look at this, there's actually something very nice hiding in here. We know if we want to maximize this with respect to theta, one option would be take the derivative of this with respect to theta, set that derivative equal to 0, right, and then confirm that it's a max. Right? But let's avoid that. Let's avoid that. All right, so let's take a look at it. You have v0 times 2 cosine theta sine theta over g. Now, I am just writing this conveniently. Oh, v0 squared, forgive me. All right? I am writing this in this way because I want you to look at this expression and say, oh, I know what that equals. Okay? That is equal to the sine of 2 theta. Okay, so here's the non-calculus way to figure out what theta should be in order to maximize this expression. I have some constant v0 squared over g being multiplied by a function of theta. What I need to figure out is what makes that as big as possible. Well, we have an advantage. We take the sign of any quantity. We know it has to be bounded by 1 from above and negative 1 from below. Right? But if we want this expression, this whole expression, to be as large as possible, we want to maximize that, then clearly we want this thing, sine of 2 theta, to equal 1. That's the biggest that expression could ever be. But what value of theta does that? Well, 45 degrees. And that is the reason why 45 degrees would yield the maximum horizontal distance